good afternoon, or good morning, depending on where you are, to everyone. Thank you very much for being with us today to the new event of the Hypatia Colloquium. Let me remind you very quickly again that there are two ways to participate today in this colloquium. Is one through the Zoom meeting, and people in the Zoom meeting, they will be allowed to make questions to the speakers using the chat when the chair of the session will give you the word, or if you are on YouTube, you can send your question and comments using the live chat that is available on the web, or you can also send the questions or comments to the speaker using the web. There is a web form that can be used. The link is posted on the chat. You can click on the link, you go to the web, there is a form, you can fill it and send it, and we monitor it constantly, and so we can send the question to the speaker. Again, let me congratulate to the speakers of today for being with us, and we are looking forward to hear the science. That's why I would like to very quickly go immediately to leave the word to our chair of today, Anna. She is a fellow at Chile, so thanks. Actually, she is very early in the morning joining us from Chile. She's an Anna Escorza. She's an expert in binary star stellar evolution, so it's brilliant scientist. So thank you very much for being with us and for chairing the session. And I leave the word to you. And thanks, and looking forward for this event again. Thank you very much.
Yeah, thank you. So hello, everyone. Yes, I'm going to chair this colloquium today, and we have two wonderful speakers for today. The first one is Anke Arentsen. She is at the Observatoire astronomique of Strasbourg in France, and she is going to present a seminar entitled Exploring the Metal Poor Inner Milky Way using the Pristine survey. So I will leave the word to her.
Thank you. Can you see my screen?
Yes, I can see it.
Okay. Yeah, thank you very much for giving me the opportunity to speak at this great colloquium series. And I look forward to sharing with you some of the work I've been doing in the past few years. So the work I'm presenting in this talk is done in close collaboration with Elsa Starkenberg, who's my PhD supervisor, and Nicolas Martin and David Aguado, and many other people in the Pristine collaboration. So my research interest is in metal poor stars and what metal poor stars can tell us about all the different components of the Milky Way, the halo, dwarf galaxies, streams. And in this talk, I will focus on the inner parts of the Milky Way, so the galactic bulge. And I'll share with you the work we've been doing on exploring the metal poor inner Milky Way with the Pristine survey. So stars are really great messengers from the past. And in the very early universe, before the first stars started to form, we have a very simple composition. We have hydrogen, helium, and some lithium. And the very first stars formed from this material. And these stars were very massive, likely, and they didn't live for very long. So we cannot observe them anymore today. But their descendants, the stars that came after the first stars, they could form smaller stars because there were traces of metals around. And these stars can survive throughout the history of the universe, and we see them as very low metallicity stars. Because through the history of the universe, we have, on average, an increase in the metallicity of stars. And stars of all these different epochs and metallicities can currently be found in the Milky Way. And if we look for the most metal poor stars, they can tell us something about the very first stars. And they can also tell us a lot about the formation history of the Milky Way. So throughout this talk, I will use the standard stellar metallicity scale for stars, which is a logarithmic scale compared to the sun. So most of the stars in the Milky Way are in this range from -1 to +0.5. And those are mainly the disk and bulge stars. Then if we go in lower metallicity on this scale to the very and the extremely metal poor stars, we find that it's about 1% of the stars, and they're mainly located in the galactic halo. But we can go even further on this scale to the ultra hyper mega metal poor stars. And these stars are the rare remnants of the first stars. And that there are only about 40 stars known currently below metallicities of -4. So each of these metallicity ranges can teach us different things about different components in the Milky Way. So I'm looking at the inner galaxy and the bulge region. And here we see that most of the metal poor stars are actually not found in the bulge. The halo is on average more metal poor. So why would we look for these stars in the inner region of the Milky Way? So the metal poor inner galaxy is interesting for various reasons. So first of all, we expect that the stars that are metal poor in the inner galaxy are extremely old. So here I'm showing a result from a simulation of a Milky Way type galaxy, where the color coding is the fraction of old, very metal poor stars. And we see that it's very centrally concentrated in the inner few kiloparsec. And this is similar in other simulations. So if we want to find the oldest very metal poor stars, we should look at the inner region of the Milky Way. And the inner galaxy is also interesting for other reasons. So here is a very nice artist impression of the Milky Way. And I like this especially because of the shape of the bulge that we can see. And this is often called the boxy peanut-shaped bulge. And it's currently the consensus that this component likely formed from an instability in the galactic disk. So it consists basically of disk stars. And we can see this in the rotation of these stars. So here I'm showing the galactic longitude versus the mean velocity. And we can see this very clear rotation curve of these stars. So then there's also been a debate for a while whether there is a classical bulge, so a pressure supported component versus a rotationally supported component. And likely there cannot be a very large one, because otherwise we would see it in the larger velocity dispersions. But it might be more important at lower metallicities. And then there may be some other remnants of the disk. And of course, we also have the extension of the halo. The halo is around the Milky Way, but it has actually its highest density in the central regions. And we don't really know what this picture looks like in metal poor stars. So the oldest stars and what they are doing. So that's another reason to look for these stars and study them in the inner galaxy. But this is quite challenging for various reasons. So first of all, there's a really high extinction. If you want to look towards the center, there's this big lane of dust across the sky, which obscures our view. And secondly, it's very crowded. There are a lot of stars to choose from. And the main problem is that most of these stars are quite metal rich. So here we have the metallicity distribution of a typical bulge survey, and they're almost all above metallicities of -1. And so if you want to get a good sample of the lowest metallicity, the oldest stars, you need to have some pre-selection. You can't just hope to get a large number of them by randomly targeting stars. So this is where the Pristine survey comes in. So the Pristine survey is a photometric survey using narrowband photometry in the calcium HK region. So here I'm showing the filter curve and the calcium H and K lines. And these lines are very sensitive to metallicity, even at very low metallicities, as seen here in the figure. So the photometry in this narrowband filter is sensitive to the metallicity. And if we combine it with broadband photometry to get an idea of the temperature, we can make a color diagram where we have this calcium HK magnitude on the y-axis, giving us the metallicity sensitivity. And we see that the metal poor stars separate very nicely from the metal rich stars. So if we want to follow up metal poor stars with spectroscopy, we can just select stars that are in the upper part of the diagram and very efficiently deselect the more metal rich stars, which is especially important in metal rich regions as the bulge. So the Pristine survey has mainly focused on the halo and dwarf galaxies, but during my PhD, we started a project to look at the bulge region. So this is called the Pristine Inner Galaxy Survey, or PIGS. And the goal of PIGS is to find many of the oldest metal poor stars in the Milky Way, which probably reside in the inner regions, but also to study the metal poor tail of the bulge in the inner halo, which we don't really know what it is doing. So the PIX data we have gathered, here I'm showing the photometric footprint, which was being collected from 2017 to 2019. And it's covering a region around the bulge where we're avoiding the plane of the Milky Way, because the extinction there is really high, making it extremely difficult to do photometric selections. And we're also observing only the northern part of the bulge, because we're observing with the CFHT, where the filter is, which is in the northern hemisphere. So we've also done spectroscopic follow-up in much of the same parts of our footprint, and we've collected about 12,000 spectra of candidate metal core stars, and we finished this last year. So we did the observations with the AAT in Australia using a multi-object, so we can get a lot of stars at the same time. And the advantage is that we get two parts of the spectrum simultaneously. So we get low resolution spectra in the optical range and higher resolution spectra in the calcium triplet. And we can use this to get stellar parameters and radio velocities for all of the stars. So then how efficient has our selection been, and how is our final sample compared to known bulge surveys? So here I'm showing again the metallicity scale. And on the right-hand side on the top, I'm showing the relative number as a function of metallicity for two typical bulge surveys, Apogee and Argos. And they're really metal rich. And in the bottom, I'm showing the absolute number of very metal core stars, so stars below metallicies of -2. And there are just barely any of these stars in these surveys. So the pioneering survey looking for metal core stars in the inner galaxy has been EMBLA, who have been using similar kind of photometry to Pristine, the sky mapper photometry. And they have succeeded at finding, for the first time, a large sample of metal core stars and even very metal core stars in the inner galaxy. And we've learned a lot from their strategy and applied it to the Pristine photometry. And we've been even more able to go to lower metallicities. And we have barely any stars with metallicities above -1. And also we have a huge number of very metal core stars, the largest sample of these stars in the inner galaxy, with almost 2,000 stars below -2. So this is a really great sample for different things. We can do high resolution follow-up, which is currently ongoing. But I will present two science cases with the low resolution spectroscopy that I've presented. So first of all, we can look at the kinematics. How do these stars move? And what we know about the metal core in the galaxy and the kinematics, in previous surveys, there were some stars at low metallicity. For example, this is a rotation curve from the Argos survey, where they grouped all of their stars below metallicities of -1. They didn't have enough stars to group in smaller bins. And they see a slightly slower rotation, but they have quite large uncertainties as well. And then a different survey looking at metal core stars is the Brava survey, where they use Lyra stars, which are typically more metal core. And here they're comparing in color the velocities for the Lyra stars versus normal bulge stars, which have this clear rotational signature. And they also don't see it in the Lyra, which they interpret as a hint that there may be a classical bulge component in the inner galaxy. So with PIX, for the first time, we can really bin this up as a function of metallicity and see what is happening to the rotation curve if stars and stars get more metal core. So our most metal-rich bin, which is typically the more metal core bin in other surveys, we don't have as many stars because this is not our strength. But we still see this signature of the rotation curve. And then if we go to lower metallicities, -1 to -1.5, we very clearly see that the rotational signature is less than the models, which are the lines in these diagrams, which are the typical metal-rich, what the metal-rich stars are doing. And then if we go to even lower metallicity, we see another decrease, and in our lowest metallicity bin, below -2, we see that there's almost no rotational signature left, and the dispersion gets larger. So at the same time we see this galactic decrease in galactic rotation, we see an increase in the velocity dispersion. So here, as a function of metallicity, we have the velocity dispersion, and it goes up very, very rapidly as a function of the metallicity. So what we might be seeing here is a transition between the boxy bulge, which is rotating and more metal rich, and the more metal poor halo, it's in the inner galaxy that is not rotating or not rotating as much. But there can also be some other processes that play a role. For example, how exactly did the boxy peanut bulge form, and what did that do to the metal poor stars? And maybe there's also an influence of the bar in the inner galaxy that maybe spins up a halo that was not rotating before. So we have some hints now of what's going on, but with just the metallicities and the velocities, we cannot disentangle these different things. And we're hoping to do this a bit more in the future by looking at the individual orbital properties of all of the big stars. So that's ongoing, and we'll continue this. But for the remainder of the talk, I want to focus on the second science case, which is the lowest metallicity stars. So stars below metallicities of -2 in the PIGS sample. So these stars supposedly tell us something about the very early universe, and maybe something about the properties of the first stars. And in the galactic halo, we've seen that many stars at these metallicities are rich in carbon. And we call these the carbon-enhanced metal poor stars, or CEMP stars, according to the definition shown on the screen. So on this slide, I'm showing a compilation of metal poor stars from the halo, where on the left-hand side, I have metallicity against carbon abundance. And we see the normal stars down here, but also this cloud of stars at really high carbon abundances. And the line is typically what we use to split carbon rich from carbon normal. And then on the right-hand side, I'm showing the metallicity and the fraction of CEMP stars as a function of metallicity. And we see that these stars become more and more important at lower metallicities. So this tells us something, that maybe something about them being carbon rich is related to the properties of the first stars. So there are two main groups of carbon rich stars in this diagram. So we have the CMP no stars down here, and they're called no because they're not enriched in neutron capture elements. And these stars are especially present at the lowest metallicities. And we think that is because they were born from gas enriched by peculiar objects in the early universe, such as faint supernovae, where you have a metal-free star that explodes at the end of its life, but only expels its outer layers with the lighter elements, and the heavier elements get locked up in the core. So then you can have an overabundance of carbon. Or on the other hand, another suggestion is that stars could be very rapidly spinning in the early universe. And so in their interior, some mixing processes making a lot more carbon. So this is one link between the carbon-rich stars and the first stars. But we also have this other group, which is the CMPS stars. And they are mainly in binary systems, and they have quite a clear formation scenario, namely that they are in a binary system where their companion was at some point an AGB star. And AGB stars can make a lot of carbon and S-process elements like barium, and they can be dumped onto the star we see today as carbon rich. So that is how the CMPS stars form, but there are always exceptions in different categories. So the CMP stars are important because they are links to the first stars, and they tell us something about binary stars. So what do we know about these stars in the inner galaxy? Here I'm showing a sample where the little circles are from the galactic halo, which is where we know most of the carbon-rich stars, and they're color-coded by whether they are S-rich or not. And then the star symbols, those are the only CMP stars we know in the inner galaxy to date. And we see that there's not that many, and that most of them are quite close to the division. They're not really very carbon-rich. So in PIGS, we analyze our low-resolution spectra from which we can recognize whether stars are carbon-enhanced. and we found 96 new carbon-rich stars in the inner galaxy. And those are the black points distributed in this diagram. So this is a great increase in the number of these stars. So unfortunately, we cannot know which category they belong to because we don't have the chemistry, but we can still look at the overall population of these stars. So it's great that we found a lot more, but it's interesting that the fraction of carbon-rich stars is low in pigs. So here I'm showing the metallicity versus the CEMP fraction, and in green is the literature, and in black is what we find in pigs. So especially above metallicity of -2.7 to -2, we have a very large discrepancy between the two samples. And the question is, why? Why do we see this big difference? Because it might hold important clues about the metal poor inner galaxy. So the first thing we worried about was that it could be a photometric selection effect. Here I'm showing one of the first discovered CEMP stars, and we can see these huge carbon bands throughout the spectrum, and they're literally everywhere in the spectrum. And these, of course, affect your colors. And we're doing photometric selection, so it may be that carbon-rich stars just drop out of our selection. And we've investigated this, but it's unlikely to be the full explanation. The effect is only very strong for really carbon-rich stars. And then we're still missing some of the stars. So if there's a difference in the CMP no fraction, this is telling us something about the first stars and early chemical evolution. And it may be that there was a faster chemical evolution in the building blocks that built the metal poor inner galaxy than that are building the outer halo. And if you have a bigger building block, you can have faster chemical evolution and you wipe out the signature, this carbon-rich signature, much more quickly, so you wouldn't see it anymore at metallicity of -2, for example. So if, on the other hand, or maybe also, there is a lack of CMPS stars, this tells us something about the binary properties of the population. And it may be that there's a lower binary fraction among metal poor stars in the inner parts of the Milky Way versus the rest of the halo. And one suggestion that we make is that it may be that there's a larger contribution of globular cluster stars, for which there are some indications. And we know that globular clusters seem to have lower binary fractions. So we will have to investigate this more into the future, but for now, these are very interesting pointers on how we can use the CEMP stars to learn about the metal poor inner galaxy. Then I will summarize the exploration of the metal poor inner galaxy with the Pristine survey. I hope you realize that very metal poor stars are unique windows into the past, and that they're very useful for galactic archaeology and for learning about the first stars. So with pigs, we built a sample of very metal poor stars in the inner galaxy, which has been very successful. And there are two science cases that I presented. So one is on the kinematics, where we see a slow galactic rotation for metal poor stars. And then on the chemistry side, we see a low frequency of CEMP stars. And then there's much more to come in the near future from pigs itself. We just finished a high resolution observation run with UVAS to follow up some of the most metal poor stars. And then also we'll combine this with Gaia information to get orbital properties. And in the more distant future, there will be the multi-object spectrograph foremost, which will target the bulge and also the metal poor bulge. So we'll have also a lot more information on different chemical elements for a large sample of stars. And I look very much forward to seeing that. Thanks.
Thank you. Thank you very much. Really, really interesting. Now I want to invite everyone to ask their questions either in the Zoom chat or in YouTube. But maybe while they start and they'll type their questions, I can ask you something, because I had read these results and I'm really, really interested in all these CEMP stars myself as well. I have two questions. The first one is, I'm curious about that high resolution follow-up. What are you looking for? Which stars have you picked? Yeah.
So we basically picked the most metal-poor stars for follow-up. And unfortunately, many of the carbon-rich stars were slightly too faint. So many of the carbon-rich stars are not in the sample. So it's largely carbon-normal stars that we've selected.
Yeah, and the other question is concerning these 96 new stars that you found that give you the different fraction of CMP stars, and you want to distinguish between S or no in order to see which one of those two effects is. I was wondering if there is another way to differentiate between those two. Perhaps if you have epochs, it could be like with some radial velocity. I don't know if you have thought of doing something like this to differentiate between one and the other.
Yeah, so one thing you can do is based just on the carbon abundance, because as you see, the CMP S stars slightly inhabit a different part of this diagram than the CMP no stars, so the blue and the red. So you can see that likely most of our stars are CMP S stars because they're in this part of the diagram. But then here they start to overlap, so it's a bit unclear what they are, and down here it's probably CMP no star. So you can make some distinction on that. And as for the radial velocity observations, yes, of course, that would be very interesting to do. We haven't started anything like that because it's a really big effort to start something.
Yeah.
And then also we found in an earlier paper that some of the most carbon-rich CMP no stars are also in binary systems. So just the binarity of these stars doesn't exclusively tell you which is which.
Yeah, okay, so you need high resolution spectroscopy, basically.
Hmm.
Okay, yeah, thank you, very interesting. I don't know if there is any question. I don't see anything here in the chat. I don't know if Giacomo has something from YouTube. I will take silence as no more questions. And I will thank you again and maybe move to our next speaker. Thank you very much. Really, really interesting.
Okay.
Our next speaker is Louise Breuval from the Paris Observatory, and she's going to talk about Cepheids and about how we can calibrate the distance scale using how we can calibrate the Cepheid distance scale. I will stop sharing my screen and let you share yours.
Can you see my screen?
Yes, perfect.
Okay, thank you very much. So thank you for giving me this opportunity to present my work. I'm a PhD student at Paris Observatory, and I'm working on the calibration of the Cepheid distance scale with the Gaia satellite. So first, let me remind you a few things about how distances are measured in the universe, and especially with Cepheid stars. Cepheids are pulsating stars. They are located in a region of the HR diagram called the instability strip. They are pulsating with a very constant period from a few days to 100 days. And Cepheids have a very interesting property, which is that their pulsation period is correlated with their intrinsic brightness. This property was discovered by Henrietta Leavitt by looking at stars in the SMC, which are basically all at the same distance. And she noticed that the longest periods are the brightest Cepheids. So it makes Cepheids very powerful distance indicators. So the place of Cepheids in the distance scale is shown in this figure. You can see on the left, it's the Milky Way, and the bright dots are the Cepheids. So the first step of calibrating the distance scale is to calibrate the Cepheid period luminosity relation by using, for example, geometrical methods like the parallax or eclipsing binaries. And once you have calibrated this law, you can move to the second step, and you look at nearby galaxies where you can see at the same time Cepheids and type 1a supernovae, which are also powerful distance indicators. And thanks to Cepheids, you calibrate the brightness of the supernovae. And then the last step is to look at distant galaxies on the right side. And in these distant galaxies, you cannot see the Cepheids anymore because they are too faint, but you can see the supernovae, and you can measure their distance. And these galaxies are moving away from each other and away from us because of the accelerated expansion of the universe. So in this distant scale, Cepheids are the very beginning, and we need to calibrate this relation between period and luminosity with extreme precision, because otherwise, if there is a bias or an offset in this calibration, then everything else will be biased up to the Hubble constant. So the Hubble constant is derived by looking at these galaxies, and that's why we measure their distance and their velocity by looking at the redshift. So the Hubble constant can be measured by two different methods. First, empirically, it's represented on this figure by the blue points. So here it's the value of the Hubble constant with during the last 20 years. So empirically, we use the method that I just described with a supernovae and Cepheids. And at the beginning, it was around 72, and now it's more like 74. And it was estimated with the Hubble Space Telescope and more recently with Gaia. And if you use a completely independent method, it's by using the fluctuation in the cosmic microwave background. But this method depends on the lambda CDM model, the cosmological model. So comparing the results and the Hubble constant from these two methods is a very powerful test of the standard model of cosmology. And currently there is a 5 sigma tension between these two methods, which indicates that there is potentially something we don't know behind the standard model. So my work is to investigate this tension and to calibrate the Cepheid period luminosity relation with good precision, thanks to the Gaia satellite that you can see on this picture. So Gaia is a European mission, and it is dedicated to study the Milky Way. And it gives different kinds of data. It gives photometry in optical bands. It gives radial velocity from spectroscopy. And most importantly, astrometry. That's what I'm interested in. Astrometry is the positions, the proper motions, and the parallaxes. So on this figure, you can see the method of the parallax. Basically, you look at a star at different moments of the year, and the movement of the star gives you its distance. Basically, you know the distance between the sun and the earth, and by looking at the movement of the stars, you know how far they are. So the Gaia data were published in releases. The second release was published when I started my PhD in 2018. So my first paper was based on Gaia DR2 parallaxes. It's the first work I will tell you about. And after that, in December, we received the Gaia EDR3. It's a first part of the catalog. And it's and I used this Gaia EDR3 in my second work. So first, Gaia DR2. So we noticed a few issues in this Gaia DR2. The first one is that there is a 0 point, which is a quantity that you must subtract to the parallaxes to make them correct. But this 0 point is very difficult to estimate, and it's potentially dependent on the brightness, on the position in the sky, on the color. So I just assumed one central value with a very large uncertainty. And that's the best we can do, but it's responsible for an important bias. The second issue is that the parallaxes are derived assuming that all stars have a constant color, but it's not true for Cepheids and for variable stars. So they must apply a chromaticity correction in the data reduction, and it's not yet implemented. So it's problematic because it means that the parallaxes of Cepheids are potentially unreliable. And one last issue is saturation. Gaia observes at very faint magnitude down to G equals 21. It's very faint. So for bright stars like Cepheids, there is a problem of saturation, but you can use some quality indicators to exclude these unreliable parallaxes. So with Gaia DR2, we have to find a solution to use these parallaxes without being affected by all these problems. So the solution is to look for stable stars and for faint stars so that they are not affected by saturation. And these stars, if we find them close to Cepheids, then we can have a proxy for the parallax of Cepheids. The first idea was to look for companions close to Cepheids. I found 22 candidates. These companions, as you can see on this picture, are very close to the Cepheids, but they are not variable, they are not saturated, and they are not sensitive to the contamination because they are far enough and they are resolved. So basically the parallax of the companion is the parallax of the Cepheid. The second idea was to look for Cepheids in open clusters. So I crossed a catalog of Cepheids and a catalog of open clusters. And based on the position, on the proper motion, and on the parallaxes, I found 14 candidates. Open clusters are very interesting because when we average the parallax of all the members, it gives a very precise average parallax. And the members are usually fainter than Cepheids. They are usually not variable. So we can perfectly use their parallax to derive their distance. So combining these two samples of companions of Cepheids and Cepheids in open clusters, I calibrated the period luminosity relation. So the blue points are the companions and the red points are the clusters. I mean the Cepheids in the clusters. And you can see that the dispersion is quite low. It's very close to what we would expect. And for the blue points, the uncertainties are sometimes quite high. This is because companions can be very faint, so the astrometry is not so precise. But for the clusters, it's very satisfying and the dispersion is extremely low, so it's very promising. And after calibrating this, this relation, I wanted to know the implication of this relation on the Hubble constant. So this is a table taken from Rees et al. And they derived the Hubble constant based on several anchors, which means distance indicators. They use masers, Cepheids in the Milky Way with parallaxes from HST and Hipparcos, and also eclipsing binaries. And they combine all these values to obtain a final average value. So I just took this one based on Milky Way Cepheids, which is 76. And when I replace just the parallax from HST and Hipparcos with my parallaxes of companions and open clusters, I re-evaluate the Hubble constant, and I find a slightly lower value of 72 instead of 76. So if we replace this line in the table, we get a value that is closer to the other distance indicators. It does not solve the tension in the sense that I didn't get 67 or something, but in very good agreement with the other anchors. But there is still quite a large uncertainty, especially because of the 0 point. But we expect that in the future Gaia data releases, we will have a better precision. And now I will tell you about the second work I did with the Gaia EDR3. So I studied the effect of metallicity on the PL relation, because metallicity is expected to impact the magnitude of stars. So I wanted to estimate this effect. For this, I used 3 samples of stars, 3 samples of Cepheids of different metallicities. The first one is Cepheids in the Milky Way. You can see on this map the sample of Milky Way Cepheids. So the color represents the metallicity. As expected, the metal-rich are closer to the galactic center. But these individual metallicities are not precise enough to be used individually, so I just averaged them, and it's close to solar metallicity. For the distance of these Cepheids, I used Gaia EDR3, so there is still a problem of chromaticity due to the variation of color of the Cepheids. But since we have more data, we can assume that the effect is almost averaged. There is still a 0 point to correct, but now it is better estimated. And I also used the quality selection to exclude contaminated parallaxes. And I used the Cepheid light curves with very good coverage, so that we have precise apparent magnitude. The second sample is made of LMC Cepheids. They are more metal poor than Milky Way Cepheids. And we have a distance to the LMC, which is very precise. And it was estimated based on the eclipsing binaries, represented as the yellow stars on this figure. And the color here represents the distance. It's not the same everywhere because the LMC is inclinated, so I had to correct for this little geometrical effect. And the last sample is SMC Cepheids. They are even more metal poor. And similarly, we have a precise distance to this galaxy thanks to eclipsing binaries again. And the SMC has a very special structure. It is elongated along the line of sight. So I just kept a few Cepheids in the very center of the SMC to make sure that we are not contaminated by Cepheids that are not really in the SMC. So that's the 3 samples of Cepheids with very precise distances and completely different metallicities. So with these 3 samples, I calibrated the period luminosity relation in the 3 galaxies. So here we have the Milky Way in red. The LMC and the SMC are shifted so that you can see the 3 of them. And the dashed line is the position of the Milky Way relation. So you can see that there is a difference. The more metal-rich Cepheids are brighter. And the dispersion is quite low. It's, again, what we expect. So this is in the near-infrared band, K, but I repeated this analysis in optical. And here on this figure, you can see the effect of metallicity, gamma, in mag per dex as a function of the wavelength. And I represent each band. So my work is in black, and it is compared with 2 other studies. In blue, it's the study by Vilgorsky. They find almost 0 effect of metallicity. And in red, it's the study by Giren. They find, contrary, they find a quite high effect and very important uncertainties. So my results are in the middle. I find an effect that is significant in infrared and it's not so important, almost zero in V band. So if you want, you can try to fit a straight line. You can imagine that there is a dependency between the metallicity effect and the wavelength. But to be sure, we need to repeat this in mid-infrared, for example, using Spitzer, and possibly with Gaia in GBP, RP bands, and have more points on this plot in order to derive a relation. So I will finish with a few perspectives for the future. So I hope that I can collect some photometry for the Cepheids in open clusters. As I said, this method is very promising because we have very precise parallaxes. So I would like to calibrate the PL relation in the HST bands for consistency with the extragalactic Cepheids, because when we observe in the same photometric systems, you can get rid of systematics. With the James Webb, I also hope that we can improve this calibration of the PL relation by looking at extragalactic Cepheids and uncrowd the Cepheid, which means resolve their photometry from the background contribution, which is currently quite limiting. Of course, Gaia next data will be very precise, hopefully, and we will be able to improve the calibration of the PL relation in the Milky Way. And finally, later with the ELT, I hope that we can have high resolution spectra for Milky Way Cepheids, and as well as for large Magellanic Clouds and small Magellanic Cloud Cepheids, so that we can constrain better the metallicity effect on the PL relation. Thank you.
Thank you. Thank you very much. Really interesting work as well. Once again, I invite everyone to ask questions either in the YouTube chat or here in Zoom for those of us who are in Zoom. I see a hand up. So yes, Ralph, you can unmute yourself and ask your question.
Yes, thanks for your talk, very interesting. My question is concerning the color access, the reddening of your stars. Have you looked into this, in particular to the 0 point of the Gaia, maybe? Their dependence?
Yes, I corrected the magnitudes from the reddening. Is it what you mean?
Yeah. First of all, is there what is the amount of the EP minus V of the color access to the sample you are studying?
In the Milky Way, it's up to 1.
Okay.
But since I'm working mostly in infrared, the effect of reddening is not so important. We are trying to use Wesenheit relations so that the reddening is cancelled. So that's one idea we can do to limit the impact of the reddening.
Okay, thanks a lot.
I don't see more hands or more questions, but maybe I can ask you a naive one. You mentioned that Gaia DR4 will help. I was wondering if Gaia DR3 already will make an impact, first to flag the binaries that could be maybe contaminating your sample, and of course more accurate parallaxes. Do you think it will help you as well?
Yes, I already used the Gaia EDR3 and it's improved in precision. The 0 point is better estimated. And hopefully in the next releases, the chromaticity correction will be implemented. So yes, we can already see that the parallaxes from Gaia are improved with time. And the more data we have, the more precise it is.
Yeah, and I think that including the binary solution in Gaia DR3 will also improve all those parallaxes and reduce the dispersion. I see another hand up. Yes, Pavel, please unmute yourself.
Yeah, hello. Hi. Could you please explain how did you select the Cepheids in the small imaginary clouds to be near the center?
I selected only a region. Let me show you the. Okay, can you see the slide?
Yes, we can see it.
Okay. I just selected a region around the center of the SMC because of its shape. I wanted to make sure that all my Cepheids are really in the SMC and really at this distance. So it's just a selection based on the position.
Because you could have a Cepheid which in projection looks near the center, but is along the line of sight on one of the quite far away from the center. So do you think that is a small chance, or did you account for that somehow?
Yes, also because I use the catalog of SMC Cepheids, so they are. This catalog has studied the position of these Cepheids, and they are expected to belong to the SMC.
Right. Okay.
But
okay, but you're not certain that you could have a Cepheid projected on the center, but it's at the far end of the SMC. In principle, this could happen, right? Or yes. But then you would expect a larger spread in your apparent magnitude or the magnitude, the amplitude period relation, I guess. But you don't see any such effect, right?
Yes, the SMC is quite problematic for this.
It is, yeah. Mm-hmm. Yeah. Okay, thanks.
And I see that there is one more question. Yes, please, Martino, go ahead.
Hi, Martino Romagnello from ESO. Thank you very much. Very, very interesting work. Very, very interesting indeed. I have a question on this very same slide. Where did you get the metallicities from for the two clouds? And then I have a comment.
Yes. I know that you provided some average metallicities, and I think these values are from the Giren paper. He took some mean metallicities from the literature and averages all of them.
Okay, so this comes from Giren 18.
Yes.
These two values and the errors. Okay, thank you very much. Then the comment I have, which is really a comment, I think it's surprising to see from a theoretical point of view as well, that the V-band dependency on the metallicity is smaller than the K-band. Common thinking is, as you know, is that everything is smaller in the infrared for Cepheids than it is in the optical, let alone B or U. So of course, a measurement is a measurement and should not be skewed towards the expectation. I think it's still very interesting. It would be very interesting to follow up what mechanism could drive a smaller amplitude in V versus metallicity than it does in K, because it's not obvious at all how this could happen. So just as a suggestion, I think it would be interesting to understand why this could be from a theoretical point of view.
Yeah, you're right. It's very interesting, and I should try to find an explanation for this trend, because in the literature, many people find the opposite, very low effect in the infrared and the opposite in the V-band, and sometimes a positive effect even. So yeah, we should compare with the theory and find an explanation, physical explanation for this.
Indeed. And you mentioned also going more to the infrared. There was a work by Friedman et al. A few years ago where they found a reversal. So high in V, essentially 0 in K, and a reversal of the sign the redder you went with Spitzer.
Yeah.
So that's also interesting to compare. Again, thank you very much.
Thank you.
Thank you. I think that's it. I don't see more questions for now. Martino, you still have your hand up, but I think it just stayed up. So that's it. I think we can close the session for today. Giacomo had connection problems, so I think I will be the one that has to say bye to everyone. I will thank the two amazing speakers again, and wish them luck in the coming time, and ask them to come back to ESO to tell us more about it, because I'm very curious about the follow-up of these two projects. And to the audience, please come back next week. That's it. Thank you, everyone.
Thank you.
I think, Louise, you are made host, so I think you will have to stop the streaming.